And we can compare with the diameter of the cores. Since a step index fiber includes both single mode and multi mode, for single mode we have the diameter to be 10 micrometer. I am speaking about the core's diameter. When we compare that with the other of graded index fiber, it is going to be 50 micrometers. Clear? So likewise, so when we look at the propagation, how the light rays travel inside step index fiber, it is going to be in kind of meridional rays, okay, where the rays will get reflected, bounce back, and it will cross over the axis. Okay, so I'm talking about the axis of the core. So the meaning of meridional rays, it is going to reflect back and forth while crossing down the axis of the core. So that is the idea behind the light rays travel in step index fiber. Clear? And this is how it will be. So you can see a light ray propagating. So here it passes over the axis of the core. Okay, and this is how your step index fiber is being working on. And similarly, if we include single mode fibers also, you can find the light ray is going to travel exactly at the axis of the core. Clear? So this is your idea behind step index fibers light travel. So when we go for graded index fiber, it is going to change. Now the light rays are going to travel in a kind of skew or helical nature. Okay, a skew in the sense it is not going to touch my center core axis. It is going to curl over the core's diameter. That is how it is going to travel. We call those rays as to be skew or helical. Clear? And coming to attenuation, attenuation that is loss, we can find attenuation to be more in case of multi-mode step index fiber, whereas in single mode you will find it to be very much lesser because it is going to be a single ray that is going to travel in a line with the axis. We find the attenuation or losses to be lesser in case of single mode step index fiber, whereas when we go for multi-mode we find that to be high in number. Clear? Whereas when we go for this graded index fiber, we find this attenuation to be less again. And you know that in graded index fiber also, we will find multiple rays to get propagated. But the actual reason behind the attenuation to be lesser is because of the light rays will get refocused at each and every intervals of time. At an equal interval of time, you find refocusing points. Okay, and you will not find dispersion at all. This makes attenuation to get lesser in case of graded index fiber. Okay, and the next parameter what we are going to discuss is about the numerical aperture. In case of numerical aperture of multi-mode fiber, it is going to be more, whereas in case of single mode fiber, it is going to be less. See, kindly to understand that the multi-mode and single mode, what I am talking about, corresponds to step index fiber. Okay, and coming to graded index fiber, this numerical aperture is going to be less. If and finally, the signal distortion. Coming to signal distortion, this signal distortion will be more here again in case of step index fiber. You know the reason again. It might be the point of not refocusing at all. Whereas in a graded index fiber, you will find dispersion to be zero. It will be focused upon. So you will find signal distortion to be very low. Clear? These are the major differences that you need to understand in case of step index and graded index fiber. So I will repeat the points again. The first point corresponds to the refractive index. So the refractive index of the core is going to be uniform throughout the core, irrespective of the type. It may be single mode or multi-mode. Whereas in a graded index fiber, you will find what? You will find the core's refractive index value to change with respect to the radius. Okay. Coming to the diameter of the core, in case of single mode fiber, it is going to be 10 micrometers. In case of multi-mode fiber, it is going to be 50 to 200 micrometers. Am I making this clear for you? Yes? Okay. Whereas in case of diameter of the core in graded index fiber, it is going to be 50 micrometers. And coming to the light rays kind of travel, we know that in step index fiber, it is going to travel in the form of meridional rays. That means it is going to travel back and forth, where it is going to cross over the axis of the core. Okay. Whereas in a graded index fiber, the travel is going to change in a kind of skew or helical nature, where it will not cross over the center course axis. Okay. Yes. And coming to attenuation, when we speak about attenuation, your multi-mode step index fiber, you will find more, and single mode index fiber, it will be less. Okay. Whereas in a graded index fiber, attenuation is completely less. Okay. And coming to numerical aperture, multi-mode fiber, it is going to be more, single mode fiber, it is going to be less. Whereas in a graded index fiber, it is going to be completely less in nature. Okay. And I told you, refocusing of rays will not happen at step index fiber, whereas in a graded index fiber, it will happen at equal intervals of time. That makes signal distortion to be more in step index fiber, whereas in a graded index fiber, it will be completely less. So this is the idea behind, or these are the differences that you need to seek for step index fiber and graded index fiber. Am I clear for everyone? Yes. Is that clear? You find the differences for step index fiber and graded index fiber. Is that clear for everyone? Yes, no? Okay, thank you. And what we are going to discuss after this is about how the refractive index is going to change in a graded index fiber. That is what we are going to see next. Clear? So before that, we will have a small questionnaire session. So I will pinpoint the people and you need to answer the question. Clear? Okay. So we'll start with Yuvedan. Yuvedan, unmute yourself. Yuvedan. Yuvedan R. Unmute yourself.
Sir.
Hi Yuvedan, how are you?
I'm fine, sir.
Okay. Let me ask you a question. Classification. One is going to be the mechanical characteristics. Another one is going to be the transmission characteristics. Right? In mechanical characteristics, we saw what is strength, what is static fatigue, what do you mean by dynamic fatigue. Am I right? So three conditions have been discussed. It's about the mechanical strength, it's about the happening of static fatigue homogeneous, and about the dynamic fatigue. Correct? And I told you what is the difference between static fatigue and dynamic fatigue. And the last two is about the flaws that is being created. So if it is going to happen very slowly or gradually in nature, we call that as a static fatigue. Am I right? If the flaw that is present in my fiber optic cable, if it is going to increase with respect to time gradually, we call that as what? Static fatigue. When we go for dynamic fatigue, I told you, it is going to be the immediate flaw that is created, immediate bending effects that is going to be created. Clear? So this is all we have discussed in mechanical characteristics. Am I right? So after mechanical characteristics, we went for transmission characteristics, where in transmission characteristics, we started with attenuation losses. Okay, why does attenuation occur? Why does losses of optical lighting will occur? And we told you, we had a discussion that the attenuation can be found by comparing or the ratio between what? The power input and the power output. Clear? It is very simple. So understanding the power input, optical power input, understanding the optical power output, we could find the relation between these two to find or identify the attenuation that is happening through the fiber optic cable. Clear? And while coming to absorption losses, after attenuation, this absorption losses will happen through. Right? So coming to absorption losses, we had a discussion about what is intrinsic absorption, what is extrinsic absorption. Clear? So if I say intrinsic absorption, it is going to be due to the basic fiber material properties. That is going to be the imperfections while manufacturing it. Clear? So the impurities that is going to happen, or that is going to be found embedded between the fiber material. Clear? This is going to be completely about the basic fiber material properties. The imperfections that happen at the molecular structure, everything will come under what? Intrinsic absorption. So when we go for extrinsic absorption, it is going to be completely upon the impurities that is added. So here we trace the metal impurities such as iron, nickel, chromium, OH minus ions. Due to the presence of these trace metal impurities during manufacturing, we find absorption to happen. Clear? And this corresponds to what? Extrinsic absorption. Okay. So you need to understand that in case of absorption losses, the absorption loss corresponds to two things. One is going to be intrinsic absorption. The second is going to be extrinsic absorption. So in case of intrinsic absorption, it is completely due to the basic fiber material properties. Okay, the imperfections formed while manufacturing, simply because of the silica or the plastic composition, which is being used as a basic fiber material. So when we go for this extrinsic absorption, you need to understand that it is simply because of the impurities that is being present while manufacturing, or if it gets added to it. Such as we can go for iron, nickel, chromium, OH minus ions. Okay, these corresponds to what? Extrinsic absorption. And coming to scattering losses then. So when we speak about scattering losses, we have simply two classifications. One is going to be about linear scattering losses. The second is going to be about non-linear scattering losses. Is that clear? So நேத்து என்ன பார்த்தோம்ன்றதை நான் மறுபடியும் சொல்லியிருக்கேன் இல்லைங்களா? Is that clear for everyone? Yes, no? Yes or no? Okay, thank you. So for today's session, we are going to speak about the scattering losses first. Okay, after completing that, we will go for the next thing. After scattering losses, we will speak about the graded index fibers, mathematical expression, and so on. Am I clear? Okay. So when we think about the scattering losses, we need to understand two concepts first. Though these are going to be very basic, that is going to be called as linear scattering. Another one is going to be non-linear scattering. Okay, coming to linear scattering, when we speak about linear scattering losses, the first thing that is going to come to your mind, that should be Rayleigh scattering. Okay, what do you mean by Rayleigh scattering? That might be your question. So I will present you a window now. See that it is being visible for you. So here I am presenting you a window. Is it visible for everyone? Yes. Is the window visible? Okay, thank you. So when we look at this scattering losses, the first thing I told you, that is linear scattering. Rayleigh scattering is the concept that is going to come first. So what is this Rayleigh scattering? So you can see a diagram here where I will zoom in so that it will be quite comfortable for you. So this is how Rayleigh scattering might happen. So you need to know the reason first. So the reason behind Rayleigh scattering is due to the scattering of light by particles present embedded. So we are going to make an optical fiber cable containing core cladding, covering, etc. But the light is going to travel through core cladding interface, that we all know. So when we look at this Rayleigh scattering, it is going to be happen because of the scattering that is going to happen because of the molecules that are very smaller than the wavelength of light. That is what you need to understand first. So when I say Rayleigh scattering, the concept is the particles that is going to scatter my light, those particles will be smaller than the wavelength of the light. Okay, so what you need to understand is it is going to be simply because of the silicon atoms or molecules. Okay, the imperfections in silicon atoms and molecules, it is going to cause Rayleigh scattering. So it is going to scatter my light that is going to be hit through the atoms or molecules. Okay, so now the causes for Rayleigh scattering, as I say, it is going to be the physical properties of the manufactured fiber. Okay, it is all about the silicon atoms and molecules. Okay, and homogeneities that is present in the core and cladding interface. Clear? So the density variations or the density connections between the atoms and the molecules of the core and cladding, what will it do is it will scatter the light in all directions. When the light is being hit through the molecules such as which has some density variations, what it will do is it will scatter the light to back and forth. So it will scatter all over the directions. So it will create losses over. So we call that as Rayleigh scattering based losses. Okay. Now coming to the next concept. Second concept is going to be called as MIE scattering, M-I-E scattering. Okay. So these MI scattering will be because of certain reasons. So the first reason is going to be will be because of your irregularities, inhomogeneities that is present in your core cladding interface. Now we are not talking about simply the atoms or molecules, or we are not talking about the deformities or the inhomogeneities present in the molecular level. We are going to get into a higher level. Okay, these irregularities, it is going to be simply because of the molecular greater than the molecular structure. Okay, so the irregularities due to the because of core cladding interface, the irregularities found in the diameters in core cladding, or the difference in refractive indices, okay, between core and cladding, all these correspond to MIE scattering or MIE scattering losses. Clear? So MIE scattering correspond to the scattering of light that is approximately equal to the wavelength, okay, that is going to be propagated. So you might come to a conclusion here. So when we speak about Rayleigh scattering, the scattering of light will be because of the particles that is lesser to that of the wavelength propagated. Whereas in case of MIE scattering, it is going to be the scattering of light by the particles, but it is nearly equal to the wavelength of the light. Okay, and the causes of MIE scattering includes the inhomogeneities in the density, irregularities in the core cladding interface, okay, difference between the core cladding, refractive indices, diameter fluctuations, all these correspond to what? MIE scattering. Clear? And when we compare these two, the Rayleigh scattering correspond to 96% of the losses. That is what it is going to be major when compared to these two scattering effects. You will find the losses to be huge because of what? Rayleigh scattering. Understood? So this corresponds to linear scattering losses. So when I speak about linear scattering losses, you should remember that two concepts. One is going to be Rayleigh, another one is going to be MIE. So when we speak about Rayleigh scattering, it is a scattering that is going to happen because of the light rays that is going to hit my atoms or molecules. Clear? So it will be lesser to that of the size of the wavelength that is going to be propagated. Whereas in case of MIE scattering, it is nearly equal to the wavelength of the light propagated. So and the causes, you know that MIE scattering happens due to because of what? Core cladding interfaces, changes in refractive indices between core cladding, inhomogeneities in the composition of silica, and diameter fluctuations. Okay, and we also say about the strains and bubbles during manufacturing. While we manufacture, if we find any bubbles to be present in the optical fiber cable, any strains, any constraints present in the making of the optical fiber will also correspond to what? MIE scattering. So this is the idea behind linear scattering losses. Okay, and then when we speak about non-linear scattering losses, it is going to be less in number and it doesn't come into your syllabus. When we look at the fiber optic properties, all they speak about is at the maximum is about linear scattering losses. Clear? So, and I will give you some introduction about this non-linear scattering losses. So this might be useful somewhere. Okay, and when we speak about non-linear scattering losses, we don't have any certain conditions for it. Okay, so what happens? It will some photon, if it is being hit under any disturbances, what will happen is it will emit an sub photon, and it will have a different kind of direction rather than the propagated direction. Okay, that will happen in your non-linear scattering losses. So remember this: the disturbance may be of any kind that happens to create a sub photon. Okay, and that is going to travel in a different direction rather than the propagated direction. All those losses will come under what? Non-linear scattering. So these are the scattering losses that you need to understand. Okay, and then after which what we are going to study is about the dispersion. Okay, so you know about dispersion, that it is going to be very prominent in the kind of fiber that is multi-mode, right? And multi-mode step index fiber, especially. So when we look at the graded index fiber, we know that the dispersion effect is going to be very less in number, because since refocusing will happen at the anonymous number of times, we will find dispersion to be very less in case of graded index fiber. So if we say the losses that happens due to dispersion, it is going to be corresponding to what? Multi-mode step index fiber. Clear? So when you look at this dispersion effect, what does it cause? Look here at the diagram. So I am going to give a pulse train as an input. Okay, and this pulse train of input will be an optical energy. Now, this particular pulse train of input as an optical energy, as it get exposed to dispersion, what happens? The output signal changes its waveform. So when you look at the signal, a square waveform is being converted simply into a curvature as an output. So the pulse representation you can see, you can identify from the diagram. For a shorter distance, how it becomes. For a longer distance, how it changes completely. So the loss of information is very prominent for longer distances if dispersion is there. So if we use a multi-mode step index fiber for long distance travel, if we don't have any repeater stations in between, we may lose the information completely, because the complete pulse train is being converted into a continuous train here. Continuous curvy nature as an output. Clear? So this is how dispersion will happen to affect my information. Clear? Okay. Now, today's class we dealt with the transmission characteristics, and under transmission characteristics I told you about the first thing, attenuation. Okay, and then the second thing is about the absorption losses, where absorption losses corresponds to intrinsic and extrinsic. Okay, and later we discussed about the scattering losses. Under scattering losses we had linear and non-linear. So under linear scattering losses, Rayleigh and Mie scattering we have discussed, and non-linear I given you a simple introduction what will happen it is to be. At last we know about the dispersion that is going to happen to. So what kind of effect that will create over my information loss. Okay, clear? So these are the characteristics of fiber. Now, getting back to the topic of graded index fiber. So in the last class, we discussed about certain definitions, the mathematical expressions, and we had a problem to be discussed. Clear? And the problem is about the step index fiber. Right? It is about the simply about step index fiber. So when we look at ray propagation in a graded index fiber, I told you already, the radius is going to have a change in refractive index. Okay, so at the center of the axis of the core, you will find the refractive index to be higher, whereas when we move over the radius of the curvy nature of the core, we happen to have a decrease in the refractive index. That is what we see for a graded fiber, graded index fiber. So how do we relate this with that kind of mathematical expression? So that will be your next topic. So we have n of r, that is given by n1 is equal to n0 times 1 minus 2 del, which encloses r by a, the power of alpha 1 by 2. So what is this? What do we understand from this? That might be a question. So previously, in case of step index fiber, we have a simple relation that n1 is going to be the refractive index of the core, n2 is going to be the refractive index of the cladding, simply. Okay, it is not going to change at all. Whereas in a graded index fiber, we find the refractive index to change with respect to the radius covered by the core. Clear? So in order to represent that, I'm going to include the notation as we are going to have n of r. Okay, so that represents the refractive index at that particular radius of centimeter. Oh, sorry, radius of a nanometer. Okay, clear? So at particular length of radius, what is the refractive index? So that is what you are seeing here as a mathematical expression, where n1 is given by n0 times of what? 1 minus 2 delta. And you know what is delta? it is going to be the refractive index difference. Okay, is that clear? I hope it is clear for you. Okay, yes, is that clear? Everyone? So I need some answers. Okay, I don't see any answers at all. Okay, so we were speaking about greater index fibers now, the mathematical expressions. Okay, so is about step index fiber, the mathematical expressions related to what? Step index fibers completely. அதுல ஒரு ப்ராப்ளம் பார்த்தோம். இப்போ பார்க்க போறது greater index fiber. Greater index fiberல வரக்கூடிய mathematical expression. Clear? Yes, தமிழ் துர்கா.
Yes, sir. ஐயோ
என்னமா அன்மியூட் பண்ணிருக்க? என்ன விஷயம்? ஐயோ, சரி, ரைட், வெரி குட். Okay, take down this mathematical expression. It is going to be the refractive index at particular radius r. So n of r is given by n1 is equal to n0 times 1 minus 2 delta, where del is going to be a refractive difference. Okay, and it is going to enclose by r by a, power of alpha. Power of alpha. A is the core radius. Clear? A is what? The core radius. And the power of alpha. Okay, the whole enclosed by 1 by 2. Similarly, n2 is equal to n0 times 1 minus 2 del, the power of 1 by 2, the whole power of 1 by 2. Clear? Yes. And b is your radius of your cladding. So these are all the parameters that you can understand. Just see at the mathematical expression alone, you will understand the things when you look at the e-books. Clear? So now what we are going to do is we are going to find what is the mathematical expression for numerical aperture. We know the mathematical expression for numerical aperture for a step index fiber. What it is? Na is equal to n1 square minus n2 square, the whole square root. That was your mathematical expression for what? Step index fiber. Now we are going to replace the n1 and n2 value here. We are going to replace the value of n1 and n2 in terms of n0. Okay, and we know what is the value for n1 and n2 from the previous page. I'm going to enclose that. So the final expression will be Na is equal to n0 times 2 delta 1 minus r square by a square. Is that clear? Okay. Yes. If you have any questions, you might ask. Yes, you can. So you might ask me a question here. நான் இங்க இன்னும் ரெண்டு மூணு வேரியபிளுக்கு என்ன அர்த்தம்னே சொல்லல. n0 என்றது என்ன தெரிஞ்சுதா? யாருக்கா தெரிஞ்சுதா? What is n0? எக்ஸ்பிரஷன்ல n0 என்னன்னு சொல்லிருக்கனா? What is n0? What might be n0? சொல்லல நானு. n1 என்னன்னு சொல்லிருக்கேன், n2 என்னன்னு சொல்லிருக்கேன். ஏற்கனவே n1 n2 என்னன்னு தெரியும். n of r னா என்னன்னு சொல்லிருக்கேன். இல்லையா? a னா என்னன்னு சொன்னேன், b னா என்னன்னு சொன்னேன். What is n0? It is going to the maximum refractive index. So n0 is nothing but what? Maximum refractive index. Is that clear? Okay. So for understanding purposes, how the light ray travels in a greater index fiber, what they are going to do is they are going to convert this change in refractive index of the core with respect to the radius in a way comparable to that of the step index fiber. So when you look at the diagram of 2.5a, so you can look at the diagram 2.5a. So here the core's gradual change in refractive index is converted in a step manner. Okay, but we have multiple number of steps to be accompanied. So this is for your understanding. So இப்போ என்ன பண்ணிருக்கோம் அப்படினு கேட்டிங்கன்னா greater index fiberல நடக்கக்கூடிய refractive index change with respect to radius புரிஞ்சிக்கிறதுக்காக step index fiber உள்ள கொண்டு வராங்க. எப்படி கொண்டு வராங்க? We are going to have multiple number of steps, a gradual increase in refractive indexes with respect to step index is going to be equalized for what? Greater index fiber. Okay, so இப்போ என்ன கவனிச்சீங்கன்னா ஒரு விஷயம் புரியும். இதுல மல்டிபிள் நம்பர் ஆஃப் ஸ்டெப்ஸ் வந்து உள்ள இன்க்ளூட் ஆயிருக்கும். கிளியர்? So இந்த மாதிரி மல்டிபிள் நம்பர் ஆஃப் ஸ்டெப்ஸ் இன்க்ளூட் பண்ணும்போது this is how we need to understand things. This is how the refractive index with respect to the core will be. Okay, அப்போ greater index fiber நடக்கக்கூடிய change of refractive index should be comparable to this diagram. Okay, now if I send a light ray, if I send multiple number of light rays into my greater index fiber as such that is shown here at figure 2.5a, இதுல இருந்து என்ன புரிஞ்சிக்க முடியும்னு கேட்டீங்கன்னா, each and every ray with the shorter wavelength or longer wavelength with respect to the incident angle will choose a particular refractive index value and it will get reflected back to the same refocusing point. That is the understanding. Okay, since we have multiple number of steps in my refractive index, what happens if I have multiple number of rays to be projected or propagated? The rays with respect to the incident angle will choose a particular step. ஒரு particular step choose பண்ணி அந்த இடத்துல இருந்து மறுபடியும் ரிஃப்ளெக்ட் ஆகி என்ன ஆயிடும்னா அதே ரீஃபோக்கசிங் பாயிண்ட்ல விழுந்துரும். அதுதான் இதுல இருக்கக்கூடிய ஐடியா. தட் கிளியர் ஃபார் எவ்ரிவன்? எஸ், இது கொஞ்சம் புரியுது, கொஞ்சம் டவுட் தான். புரியுதா எல்லாருக்கும்? சொன்ன விஷயம் புரிஞ்சுதா? ஸோ இங்க என்ன பண்ணிருக்கோம் அப்படின்னு கேட்டீங்கன்னா, கிரேடட் இண்டெக்ஸ் ஃபைபரை ஒரு ஸ்டெப் இண்டெக்ஸ் ஃபைபரா உருவகப்படுத்திக்கிறோம். எப்படி பண்ணிருக்கோம்? இந்த கிரேடட் இண்டெக்ஸ் ஃபைபர்ல நடக்கக்கூடிய சேஞ்ச் இன் ரீஃப்ராக்டிவ் இண்டெக்ஸஸை we are going to compare to that of what? In a stepwise manner. Okay, so we include multiple number of steps in my refractive index change. When multiple number of steps include ஆனதுக்கு அப்புறம், if I project my light rays, what happens? The light rays with respect to the incident angle and after bending or refraction from air into the medium of the core, what happens? It chooses a particular refractive index. அது ஒரு particular step of refractive index choose பண்ணி it will focus upon at the same point. So what happens finally? Your light rays will travel like this. Like this. So the figure 2.6a and b, where the ray path is being shown, is your example for how the light rays is going to travel inside. Is that clear? Yes? Purjudha? Yes or no? Students, புரியலனா மறுபடியும் சொல்லுங்க. I will teach it again. My voice audible for you? Yes? No? Put it in the chat box. Okay. So இப்போ இங்க நீங்க கத்துக்கிட்ட விஷயம் ஒண்ணே ஒண்ணுதான். என்ன இப்ப இந்த மேத்தமெட்டிக்கல் எக்ஸ்பிரஷன்ல பார்த்திருக்கோம்னா, the mathematical expressionல refractive index will change with respect to the radius. Okay, so அதுக்கு உண்டான mathematical expression என்னன்னு பார்த்திருக்கோம். அந்த mathematical expression மூலமா numerical aperture என்னன்னு பார்த்திருக்கோம். Okay, the second thing is how the light ray travels in a graded index fiber. அதுதான் புரிஞ்சிக்கிட்டு இருக்கீங்க. So நீங்க எப்படி புரிஞ்சிக்கிட்டு இருக்கீங்க? The graded index fiber வந்து since it has a gradual increase and decrease in my refractive index as I move on to the center of the axis to the core radius and core radius extreme outer ring to the inside of the axis, we compare that to that of a multiple number of steps to be accompanied. Okay, அதை எப்படி கம்பேர் பண்ணிக்கிறோம்? இதே கிரேட்டர் இண்டெக்ஸ் ஃபைபரை இன்னும் மல்டிபிள் நம்பர் ஆஃப் ஸ்டெப்ஸ் இருக்கக்கூடிய ஸ்டெப் இண்டெக்ஸ் ஃபைபரா கற்பனை பண்ணிக்கிறோம். அப்படி கற்பனை பண்ணிக்கும் போது என்ன ஆகுது? லைட் ரேஸ் டிராவல் ஆகும்போது ஒவ்வொரு லைட் ரேவும் ஒவ்வொரு ரீஃப்ராக்டிவ் இண்டெக்ஸ் ஏரியாவை சூஸ் பண்ணோம். அந்த பர்டிகுலர் ரீஃப்ராக்டிவ் இண்டெக்ஸ் ஏரியாவை சூஸ் பண்ணி ரிஃப்ளெக்ட் ஆகும்போது இட் வில் ஃபோக்கஸ் இன்டு அ சென்டர் பாயிண்ட். ஓகே, a refocusing point that is shown in your diagram, that is figure 2.6b. That clear for everyone? Yes? Okay? Yes? So இதுக்கு அப்புறம் இன்னும் நிறைய mathematical expressions இருக்கு, but it is not required I think, because in your syllabus all they speak is about the understanding of the concepts. Okay, they haven't mentioned about any derivations that is need to be derived upon. Clear? So the next thing what we are going to study, so என்ன கவர் பண்ணிருக்கோம்ன்றத சொல்லிடுறேன் டிஸ்கஷன்ல. So இது வரைக்கும் என்ன பார்த்திருக்கோம் அப்படின்னு கேட்டீங்கன்னா, we have covered what is optical fiber, the advantages of optical fiber, the basic laws that govern the propagation of light with respect to ray optics. Clear? Ray optics base பண்ணி இருக்கக்கூடிய fundamental laws என்னன்னு பார்த்திருக்கோம். Okay, and certain definitions, numerical aperture, acceptance angle, critical angle. Okay, இது எல்லாத்தையும் புரிஞ்சிக்கிட்டு இருக்கோம். Okay, Snell's law என்னன்னு பார்த்திருக்கோம். and then step index fiberல இருக்கக்கூடிய mathematical expressions என்னன்னு பார்த்திருக்கோம். Then graded index fiberல இருக்கக்கூடிய mathematical expression பார்த்திருக்கோம். Okay, how to compare a graded index fiber by understanding step index fiber ன்றத பார்த்திருக்கோம். Clear? And what is the difference between step index and graded index fiber? இது பார்த்திருக்கோம். Clear? And what are the fiber characteristics, mechanical characteristics, as we speak about strength, static fatigue and dynamic fatigue. Okay, and then transmission characteristics varumbodhu attenuation, absorption losses, clear, and dispersion, scattering losses. All these topics have been discussed. Okay, now the next concept what we are going to study is about the emission of light rays from photonic sources. Okay, so to understand photonic sources, we need some knowledge about semiconductors first. So you might have studied about semiconductors, right? And what I will say is, this semiconductor industry is going to be the basic platform behind any kind of technology. Even if it is a fiber optic technology, if it is a different kind of machinery or whatever it is, the back end will be your semiconductor platform. Okay, so we need to know about what is semiconductor first to understand the photonic sources. Okay, we speak about photonic sources. I told you already about LEDs, light emitting diodes, ILDs, injection laser diodes or induction laser diodes, that will be used as your sources of light inside your optical fiber communication or fiber optics. Here, so to understand these sources working, you need to know what is semiconductor first. So what is the role of semiconductor? What do you mean by semiconductor first? So hope everyone knows what is semiconductor, right? So can someone say me what semiconductor is meant to be? What do you mean by a semiconductor? Anyone? You can unmute yourself. Tell me what is meant by a semiconductor. So, or else I need to pinpoint anyone. Will that be okay? My voice audible for everyone? Yes? Yes, no? Is my voice loud and clear? எல்லாரும் கேக்குதா நான் பேசுறது? Kindly put it in the chat. Okay. சரி. செமிகண்டக்டர்னா என்னன்னு கேக்குறேன்பா. யார் கேட்கலாம்? Okay, we'll start with Tamil Durga. Tamil Durga, unmute. What do you mean by semiconductor?
Sir, partially வந்து conduct பண்ணும் sir.
Partially conduct. Okay, very. அது என்ன partially conducting நம்ம புரிஞ்சுப்போம். Okay. We have Robin வீட்டுக்கு போயிருப்பாருன்னு நினைக்கிறேன். Robin, unmute. Robin. இன்னும் டிராவல்ல தான் இருக்கான் போல இருக்கு. Very good. Beautiful. So whom we have here? Santosh Ruban. Can you unmute yourself? Santosh? Santosh Ruban Raj. Oh, Santosh இல்ல போல இருக்கே. Yes sir மட்டும் போடுறான். Unmute பண்ண முடியலையா? Unmute பண்ண முடியலையா? Noisy. சரி. சரத் பாபு, சரத். நாளைக்கு வரும்போது என்ன பண்றீங்க? உங்க மைக் எல்லாத்தையும் செக் பண்ணிட்டு வந்துடுறீங்க. I'll be asking questions in between. That makes our class more interactive. Okay. Sharad, what do you mean by semiconductor, Sharad?
The semiconductor material have conductive between conductors.
Abba?
Conductivity between
conductor and insulator. சரி, இதுல இருந்து என்ன புரியுது அதுதான் எனக்கு தெரியணும். When we speak about semiconductors, Tamil Durga said that it is going to partially conduct. இப்போ பார்ஷியலா கண்டக்ட்னா என்ன அர்த்தம்? பார்ஷியலா கண்டக்ட்னா இப்போ 10 ஆம்பியர் கரண்ட் கொடுக்குறேன். இப்போ ஒரு 2 ஆம்பியர் கரண்ட் வந்து கண்டக்ட் பண்ணுச்சுன்னா இட் இஸ் பீன் பார்ஷியலி கண்டக்டிங் அர்த்தமா? தமிழ் துர்கா, அன்மியூட் யுவர் செல்ஃப். தமிழ் துர்கா காணும் போலயே.
எஸ் சார்.
பார்ஷியலி கண்டக்டிங் சொன்னீங்களே,
ஆ
கொஸ்டின் என்னன்னா இப்போ 10 ஆம்பியர் கரண்ட் இருக்குமா, அதுல 2 ஆம்பியர் கண்டக்ட் பண்ணுது பார்ஷியலா,
ஆ
செமி கண்டக்டர்னு சொல்லுவோமா எப்படி?
ஆஹா அப்படி கிடையாது சார்.
அப்ப என்ன மீன் பண்றீங்க? A semiconductor acts both as an insulator and conductor, correct?
Yes sir.
So it requires a control signal. At one point of time it is going to act as what? A conductor. One point of time it is going to act as what? Insulator. So partially conducting நம்ம சொல்லக்கூடாது இந்த இடத்துலயுமே. Okay. It is going to act both as what? Insulator and conductor. Clear?
Yes. Yes sir.
Okay. Yes. So when we deal about semiconductors, we know about p-type and n-type semiconductors. Okay. Semiconductor nu sollitomna adula varakoodiyadhu p-type and n-type nalla theriyum. So what is p-type? What is p-type semiconductor mean? What is n-type semiconductor mean? So can anyone unmute yourself and answer me? We are having an interactive session. Please. இது புரிஞ்சிச்சுனா அப்புறம் நம்ம photonic sources பத்தி நிறைய பார்க்க முடியும். Quick. இல்ல நான் பின் பாயிண்ட் பண்ண எதுவும் சரி பின் பாயிண்ட் பண்ணிடுவோம். யாரும் கேட்கலாம். ரூபன்.
Yes sir.
Good morning Reuben, how are you?
Fine sir.
Okay, tell me what is p-type semiconductors? What do you mean by n-type is?
In p-type semiconductors, the carriers are positive atoms.
Positive atoms or positively charged atoms?
Positively charged atoms.
Okay, if we have an atom, the outer bound will be your electron, right? The outer shells will be accompanied by electrons. If I remove an electron, the atom becomes what? Positively charged. We call that as holes, right?
Yes sir.
The removed electron will be called as what? Negative charges. Correct?
Yes sir.
Okay. So why do we have this p-type material to be created? So semiconductor na என்னன்னு தெரிஞ்சதா இல்ல ஏன் p-type n-type னு நம்ம கொண்டு வரணும்பா?
No.
What is the reason behind? ஏன் p-type n-type னு இருக்கணும்?
That's sir.
தெரியல. Okay, thank you. வேற யார் கேட்கலாம்? சங்கீதா இருக்கீங்களா?
Yes sir.
சொல்லுங்க சங்கீதா. Why do we have p-type and n-type semiconductors?
So in p-type, majority carriers are holes, so they move from higher potential to lower potential.
Rita,
Yes sir.
I'm not asking the question what is p-type and n-type. Why should we have p-type and n-type separately? That is the question. ஏன் p-type and n-type னு பிரிக்கணும்? அப்படி பண்ணலைனா என்ன ஆகும்? சரி, நிறைய நம்ம டிவைசஸ் படிச்சிருக்கோம் இல்லையா?
Yes
The
sir.
first most
Yes,
you will see your diode, correct? PN junction diode. Correctங்களா?
Yes sir.
Is that a semiconductor or not?
Yes sir.
Yes. Okay. So it is a semiconductor device. It is going to conduct at one time. It is not going to conduct at another time. It will have a different kind of control signal. Correct?
Yes
Yes.
sir.
Okay. எந்த டைம்ல PN junction diode conduct பண்ணும்?
Forward bias.
Forward bias. Okay. So அப்ப நான் forward bias கொடுத்த உடனே conduct பண்ணிடுமா? Conduct பண்ணிடுமா? Okay,
Yes.
think. Very good, very good. Thank you, Sangeeta. Sandhya is present. Unmute Sandhya. Sandhya P. Sandhya? இல்ல. சரி. Sandhya M. Sandhya M. இல்ல. சரி. Okay. Subhash இருக்காரு. Very good. Subhash, unmute.
Yes, sir.